All right, so one of the things that you are learning this week in the many sections that you guys have to read is the distance formula. And so the book does cover sort of how we get the distance formula, but I think that it doesn't fully explain, like they use absolute values, which could be confusing, and it really doesn't necessarily matter. So I thought that I would start by going through kind of showing where the formula comes from, and then we would do some examples just so that you see how it's used. So first off, the distance formula is something that you are going to know. You're going to need it when you get to calculus. It's just going to be something that you will kind of want to memorize. It's x2 minus x1 squared plus y2 minus y1 squared, and then square root over that whole thing. So let's say we just have two ordered pairs. So I'm going to call this first one x1, y1, and the second one x2, y2. And so our distance formula is finding the distance between it, and it's finding the shortest distance between it. So if you were to, connect those with a straight line. And the way we get the formula is actually by using the Pythagorean theorem, because we can visually make a right triangle here. And then using the Pythagorean theorem, you can basically solve for the length of the hypotenuse, which is going to be that distance. So we have this third order pair that we're kind of creating here, which is x2, y1, because it's got the same value, same x value as x2, y2, same y value as x1, y1. So that's like our third point. And so the distance, the lengths of these, when you have just horizontal and vertical, the length is basically the difference in either the y or the x. So the horizontal distance is x2 minus x1, because we usually just take the right minus the left. So that is the distance there. And then the vertical is y2 minus y1. So we just take the top minus the bottom, basically the bigger minus the smaller. So the order here doesn't really matter. So we've got this triangle that we've kind of drawn, and we're going to use the Pythagorean theorem to find that unknown distance. And so the Pythagorean theorem, just as a reminder, because it actually comes up a lot with algebra, is a squared plus b squared equals c squared. So if you have a right triangle, a, b, c is the hypotenuse. So we're going to plug in our distances in purple into the Pythagorean theorem and then solve for the unknown distance, which we will call d. So we're starting with a squared plus b squared equals c squared. And if I redraw the triangle that we have, this is x2 minus x1, y2 minus y1, and then d. So we have x2 minus x1 squared plus y2 minus y1 squared equals d squared. And all we want is d, so you just simply have to take the square root of both sides, and that's where we get the distance formula. So it's actually quite simple to get the distance formula once you know what's going on. And so if you always forget how to find the distance formula, just remember it's coming from the Pythagorean theorem. But I wanted to kind of work through this because in our textbook, it uses absolute values, and then suddenly in the formula, the absolute values become parentheses, and it doesn't really explain why that is. And that's because, so they use absolute values just to explain why the textbook does this, is distance is positive. And so they just put absolute values around these just to make sure that we're going to get positive numbers, because distance is never negative. And then basically when you square something that's positive, you're going to get a positive out. So then we don't need the absolute values anymore, because even when you square a negative, it's going to become positive. So then they kind of drop the absolute values once they do the squared part, because then they don't matter anymore. So that's why the textbook kind of first puts it with absolute values and then they disappear. And I don't even bother using the absolute values, because you're going to square it anyway. It just kind of seems silly to put them in there and then they're going to disappear. So yeah, it makes sense, because I don't know how many of you actually read the book carefully, but you might have looked at that and then been like, well, what happened? So that's what happened, basically, is that we said, oh, we don't actually need absolute values. We'll just drop those. So that's where the distance formula comes from. And so we're just going to do some problems using the distance formula. And frequently when you use the distance formula, if it's not a word problem, you're going to have square roots and that you're going to have to simplify. And I know a lot of people struggle with simplifying radicals. So I thought this is another good thing, just to keep practicing this. And then I actually do have some word problems, so you can see where the distance formula is useful. But first, we'll just practice using the formula. So we're going to find the distance between 8, 5 and 2, -1. So it doesn't actually matter which ordered pair you label as x1 and x2, but I just always do it in order. And just to help you memorize the formula, it's always good to write it down every time. And just make sure that your square root does cover the whole thing. If you end your square root early, then technically you're not using the right formula, because that whole thing is inside that square root. So we subtract the x values. So we got 2 minus 8 squared plus, and then the y values, -1 minus 5 squared. And sometimes what I'll do is I'll actually add the square root last, so I know how long to make it, instead of drawing it first. So 2 minus 8 is -6, so we have -6 squared. -1 minus 5 is -6 squared. And then I'm putting in my square root just to make sure that it's long enough. So that gives us 36 plus 36 inside the square root, which is 72. And now 72 is not a whole number when you take the square root of 72. So this is where we need to simplify radicals. And this is where people are usually like, shoot, I don't remember how to do this. So I always like to make a factor tree. So 72 is 9 times 8. And then 9 is 3 times 3. 8 is 4 times 2. And 4 is 2 times 2. So I'm just breaking it down into its prime numbers. And when we're simplifying a square root, you want things to be in even powers in order to simplify. So we've got 2 3s, so that's 3 squared. But then we have 2 cubed. But I can instead rewrite this as 3 squared times 2 squared and then put the third 2 separate. So that way I have things with even exponents. Because for the square root, you're basically dividing the exponent by 2. And it cancels out even exponents. And anything that has an exponent of 2 just basically disappears. So I'm going to rewrite this as 3 squared times 2 squared times 2. And then the 3 and the 2 with the squares, those come out. So you can take the square root. And then the multiplication is still there because all this stuff is multiplied together. And we end up with 6 times the square root of 2 as our final answer for the distance. So even though when we talk about distance, talking about it in terms of square roots doesn't really make sense because in the real world, we don't, we like to have decimals or fractions, but this isn't a real world problem. It's just specifically demonstrating the use of the formula. So we leave it in the exact form. So we leave it with the square root and we don't approximate it. Are there any questions? Okay. Now here is where the distance formula can come in handy. So we're going to use the distance formula to verify that the following 3 points form a right triangle. So basically, we're going to check to find, if we find the distance between the 3 sets of points, do they work in the Pythagorean theorem? That's how you verify that they're a right triangle, is that they work in the Pythagorean theorem. So we need to check every combination of pairs of points. So we need to check -1, 3, and 3, 5. We need to check 3, 5, and 5, 1. But we also need to check -1, 3, and 5, 1. So because we have 3 sides here, we connect these 3 points are going to be 3 sides. And so we need to find the distance between each of these. And then we need to check them in the Pythagorean theorem. Now, incidentally, there's me and 2 people on here, so we can split up the work so that you guys can practice. So each of you can pick one of these pairs. So do we have any volunteers in the chat if there's a particular pair you want to do the distance formula on to practice? Okay, so Toby's going to take the last 2. Okay, I'll just put Rick in the middle, and I'll do the first one. Actually, we've got Alexander. Alexander seems to be joining, so I will also stick him there. So I'll do the first one. So let's just all work on these, get our distances, and then we will check them in the Pythagorean theorem. And so for the one that I'm working, I'm actually doing x1 minus x2, but it doesn't matter. So I'm just doing it the other way to kind of demonstrate that. Welcome, Alexander. So I saw that you were joining. We have split up the work of the distance formula here so that everybody gets a chance to kind of practice it. The formula is D equals x2 minus x1 squared plus y2 minus y1, so squared. And then that's all inside a square root. So if you want to give a stab at the middle pair of points, so we've got 3 sides, 3 distances, and we need to check if these work in the Pythagorean theorem. If they work in the Pythagorean theorem, that means that this is a right triangle. And we should get yes that they work because it says to verify that they form a right triangle. So we'll see, do these form a right triangle? So And the thing with the a squared, b squared plus c squared is always the longest side. So square root of 10 is bigger than the square root of 5. So the third side here is the longest side, so that's going to be our c. And if you're not sure when you have them in this form, you can look at it before you simplified. 40 is bigger than 20, so that one's going to be longer. So when we have the Pythagorean theorem, we have a squared plus b squared equals c squared. Now, it's often easier to do it in the unsimplified form while it's still inside a regular square root, because it's a lot easier to square. So we could have square root of 20 plus, or square root of 20 squared plus square root of 20 squared equals square root of 40 squared. And so the square roots cancel, and we end up with 20 plus 20 equals 40, which works. So that means that, yes, this is a right triangle. So this is one use of the distance formula, is to check to see if things form a right triangle without graphing it. And if you graph it, it could look like a right triangle, but without actually measuring the angle, you don't necessarily know. So I actually, because the distance formula is not too bad, I only have one problem remaining. This is not something that you need like tons of examples for. So this is the word problem. So we've got a soccer player passes the ball from a point that is 18 yards from the end line and 12 yards from the sideline. A teammate who is 42 yards from the same end line and 50 yards from the same sideline receives the pass. How long is the pass? So for problems like this, I like to draw pictures, because I am somebody that needs to see what's going on. So I'm just drawing a soccer field, and the sidelines here. So then we've got like an end line. So I don't know which side that they're on, but if I was to label this, I'd probably put the lower left corner as 0, 0 if I was to kind of put this on a grid. And that's just because that's, distances are positive. I want to work with positive numbers. So I can just make that lower left corner 0, 0. But if you wanted to, it doesn't matter. You could make the upper left corner 0, 0, and then all of your numbers you'd have some negative numbers, you'd have some positive numbers when you're trying to, draw your grid here. I'm just picking the lower left because that makes all my numbers positive. But you could put it anywhere you want as long as you've got your distances matching properly. So I'm going to assume that when we're 18 yards from the end line, we're 18 yards from the end line that's at 0, 0, because there's two end lines here. And it would just be a lot easier to work with the one from the 0, 0 point than the one on the right. But again, it doesn't matter as long as you have all your ordered pairs in the right spot. So I'm going to say that we're right here, 18 from the end line, so that's the horizontal distance here, and then 12 yards from the sideline, which is vertical. So even though my sideline is the horizontal line, 12 yards from the sideline is actually a vertical distance. So that's why I like to draw a picture. So that way, you don't just think, okay, my sideline's got to be X. It's not. It's actually going to be the Y. Then we've got a teammate who's 42 yards from the same end line and 50 yards from the same sideline. So let's say somewhere around here. It's going to be 42 and 50. And this is obviously not to scale. This is just to kind of give us the idea of what we're looking at here. So not to scale, but now we've got ordered pairs. So now we want to know how long is the pass. And this is a problem because it's a word problem. This is a problem where you're going to actually use the decimal approximation when you take the square root, because that's what we do in real life. So I'm going to just rewrite the distance formula. X2 minus x1 squared plus y2 minus y1 squared inside a square root. And so I'm going to make x2 the 42, the point with the 42. So we'll do 42 minus 18 squared plus 50 minus 12 squared. So 42 minus 18, pulling out a calculator, 24. So that's going to be 24 squared, and then 50 minus 12 is 38. So that's going to be 38 squared. So 24 squared is 576. 38 squared, 1,444. Add those together and we get 2020, incidentally. Now, we're going to actually just take the square root of 2020. And so that gives me about 44.94441,011. Those are the numbers that I see on my calculator. So we're not told how much to round this to, but I would probably round this to a whole number, which would be 45, and say it's about a 45-yard pass. We have to include the units. We want to, write this as a sentence because it is a word problem. So let's say the pass is about 45 yards long. We certainly are not going to say it's the square root of 2020 long. That's not going to be useful in real life. So the distance formula is something that you can use in, like, if you have a graph or you have a grid, you have a map. I mean, with GPS coordinates, you can even use the distance formula if you wanted to find the direct distance between 2 points that are, if you have them on a map, you can do that and you can find the direct distance. So it's actually a very useful formula, especially if you're someone that's like hiking and relying off of GPS and, going off the grid or something. You might want to use this so okay, what's the shortest path? How long is that going to be? You can plan ahead, make sure that it's something you can do in a day or whatever.